welcome to chapter 5.1. We've got 3 sections in chapter 5. It all deals with probability and probability rules and what else? Venn diagrams, chance, conditional probability, and independence. All sorts of fun stuff. So let's start off with randomness, probability, and simulation. And simulation is a very specific thing. It's a 4-step process, and this is definitely an FRQ concept right there. So moving forward, in this particular section 5.1 or 5.A, we should be able to interpret probability of a long-run relative frequency and use simulation to model chance behavior. And this is a very specific, again, it's very detailed. How do I do it? And when we're talking about this in terms of free response questions, you need to be as detailed as possible when doing these types of questions. And I've got an example for us that I will flag it in that moment to be like, hey, this is definitely kind of a question that could easily be attributed to an FRQ. So the law of large numbers says if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. Fun, long, formal definition. I'll talk about what it means in just a second. But the real definition that we want to focus on here is probability. It is any outcome of a chance process is a number between 0 and 1. And so that's really that probability you guys are used to. I have a 1 in 7 chance of succeeding on this, or I have a 1 in 50 chance of grabbing this color marble from a jar. You guys know that as probability. A probability of 0 means there is no chance of it occurring. But how do we understand the law of large numbers? Let's go to something that we understand very easily. Let's go to a coin toss, which is exactly what those 2 graphs are behind my little character is doing. And what it is, so let's say I flip a coin, and what is my probability of getting heads? And you would tell me you have a 1 in 2 chance or a 50-50 chance of getting a heads or tails, depending on which one you're looking at. And so let's say we're talking about just heads, because that's what these graphs are talking about. So at the beginning, I might get heads and then tails and then tails and then tails and then heads and then heads and then tails, whatever. It's all sorts of chaos. And as you can see at the beginning of our graph, you can see we've got some chaos going on here. It looks all over the place. And at the beginning of this graph, it's all over the place again with those tosses. But as you can see, as I get to a very large number, interesting, a very large number, part of that law of large numbers, our proportion becomes 0.5. It evens out about here. So what they're saying is over the course of lots and lots and lots and lots of repetitions, we actually get to see the true behavior that occurs from that probability that you calculated for yourself. 1 in 2 chance is 0.5, and so it occurs when you do repetition huge number of times. But because of this law of large numbers, we end up with some myths. And so I want to address those really quickly. There's 2 myths that we want to talk about: the short run regularity. And so that's, if there's a 50-50 chance that I'm going to get heads and I've gotten tails numerous times, then of course heads must be next. This is the myth of short run regularity, that you believe that because you know what the rule and law is becoming, you assume that it must occur, and you forget that random phenomena is part of predictability. So thinking of this in terms that you would understand, I'm taking a multiple choice exam, and every answer is B. Question 1 is B, and question 2 is B, and question 3 is B, and I get to question 4 and 5, and I'm like, oh my God, they're still B. And I know my teacher probably randomized these answers, so how are they all B? Did I make a mistake? The reality of it is I can run a random number or a random answer generator, and I can get what we call a short run, a bunch of B's in a row. And that's okay. That's still part of randomness. That is still the chaos of randomness. Runs can occur, but I can't predict. I can't say, well, if these are all B's, my next question better not be B. You as a student know that that's not how multiple choice tests work. The answer is simply the answer, whatever pattern is occurring on my answer bubble sheet. All right, the myth of the law of averages. So probability tells us random behavior evens out in the long run. We know that, but our future outcomes cannot be affected by past behavior. Where we see the law of averages occur really often is what we call the hot streak in gambling or wherever else you might see that. But I won 3 times in a row. I must be on a hot streak. I'm going to win again. Or vice versa. I just won 6 times in a row. This table's over. There's no more wins left at this table, but it's got to be a losses coming next. That would be the law of averages that you're using inappropriately. It doesn't work that way. Another place, there's a silly little joke. I don't know if this is a real story or if it's just to make this comic strip make sense. But so the law of averages doesn't guarantee me a girl after 7 straight boys, but can't I at least get a group discount on the delivery fee? So this little story goes that a woman comes in and she's had girl after girl after girl, and the doctor is like, okay, you've had 7 straight girls. Theoretically, the law of averages say that the next one, it should be a boy because you've had 7 girls, so the next one better be a boy. Well, guess what? Baby number 8 was still a girl. And so the law of the law of averages can trick us into thinking that past behavior can influence the future, but the reality of it is it doesn't work that way. So myths about randomness that I wanted to just pause for a moment and talk about. So let's get into simulation. Simulation is a very specific way to model chance behavior. I'm sorry, there's something stuck in my throat. Sorry. Simulation is a way to model chance behavior, and it takes 4 steps to do it. You first state, plan, do, and conclude. And so you can read about this, or you can check your textbook about this. We have done simulations, every one of our experiments so far, where we had dice or random numbers or calculator for random numbers or anything like that. We can use that for simulations, and we've done those in the past. But let's go ahead and do 2 simulations very quickly together. This first simulation is dealing with Table D in the back of your textbook. So if you're following along in class with a textbook, that's in that back after the formulas and everything, and it looks like this. Okay, so there's our Table D, and I've got a little snippet of it. But, if you're not near a table or whatever, you can either Google it or you can just follow along real quick. So at a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at a school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP Statistics class. When both golden tickets went to members of the same class, some people thought the lottery had been rigged. There are 28 students in your AP Statistics class, all of whom are eligible to park on campus. So, design and carry out a simulation to decide whether it's plausible that the lottery was carried out fairly. So, state, plan, do, conclude. Let's do those. What is the probability that a fair lottery would result in 2 winners from the same AP Statistics class? Plan. We're going to use the table of random digits. We're also going to do another simulation using the calculator's rand integer thing, but we never really got to use the Table D, and I know that it's going to show up on the AP exam potentially under the FRQ section, so I did want to just showcase really quickly how we use this. So I'm going to plan. And if this was a free response question, this is one of the most important steps right here, because if my plan written out cannot be recreated with all of the steps accounted for without any, assumption, inference, or anything, it was 100% clear, then that's a good free response question. If you've left anything for me to figure out for myself, that's a bad answer and you're going to lose some points. So I want you to notice how detailed this plan already is. So all these steps are very detailed. Since there are 95 eligible students in the lottery, we'll label the students in the AP Statistics class. Already, so many details are included. We'll label the students from 01 to 28. And the remaining students from 29 to 95. So I didn't just say label the students from 1 to 95. I was very specific. Numbers from 96 to 00 will be skipped. Again, very specific. We're skipping those because there are only 95 eligible students. So we're not leaving that up to our imagination. We're saying it clearly. Moving from left to right across the row, again, I'm saying very clearly how I'm using Table D, the table of random digits. We'll look at pairs of digits. Detail, pairs. We'll look at pairs of digits until we come across 2 different labels from 01 to 95. The 2 students with these labels will win the prime parking spaces. We will record whether both winners are members of the AP Statistics class using yes or no. This is a very well written and well thought out plan because it doesn't leave anything to my imagination. I know exactly how to run this plan. So I go, here's the do. Let's perform many repetitions. We'll use the table starting at line 139. Why line 131 and 39? It's random. I could have put in the back of our textbook, we have lines 101 to 150. I can put that into a random number generator and grab a random number again. I can just point my finger and pick a random line. It doesn't matter. We just picked a random line at 139. It could have come from a random number generator though. So I'm looking at line 139. The digits are shown below, and that's what this is right here. There's line 139. And this is what we're going to eventually do, is separate them out. I was just giving you a preview of both what it looks like in your table and what it's going to look like on our experiment. So here I have, this is line 139, but I've split them into 2-digit numbers because that's what we're using. 0, 1 through 95 are 2-digit numbers. So here, 55 and 58. This is repetition 1. No, because none of those are our AP Statistics students. 89, 94, not our AP students. 4 is an AP student, but 70 is not, so that's a no, where we don't get both of them AP students. 70 and 84 are non-AP students. 10 is an AP student. 98 is outside parameters, so I skip it. So it's not 10 and 98, it's actually 10 and 43, but in order to have transparency, I'm going to write 98 as a skipped value. So repetition 5, again, has not 2 AP students. 5335, not 2 AP students. 6934, not 2 AP students. 4839, 45. So at this point, in the first 9 repetitions, no winners have ever been from the AP Statistics class. And we know that because those numbers would have been from 1 to, I think it was 28 or 26, right? We can check. 28. There are 28 students. Okay. But let's keep going because we're not just going to do 9 repetitions. We're going to do, I think, 50 total. But we can, keep on showing. So here's repetition 10 through 18. And here you can see 19 and 20 were both selected. This would have been an instance where 2 AP students got selected at random. Here we have no, 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 no. Here's another yes. No, here's another yes. And again, this is just using the table of random numbers. They are already randomized. So in just 18 repetitions, I've already got 3 instances where 2 AP students could have been selected at the same exact time. So if we kept on going, and I think they did a total 50 of repetitions, they got a total of 5 yeses and 45 nos. Well, so do you think that it was fair? If 5 different instances of random numbers gave me 2 AP students winning the golden ticket lottery at the same time, then is it plausible? I would say yes. 1 in every 10 times the student council holds the golden ticket, it'll happen just by chance, so it does seem plausible. So that would be a good concluding sentence. Well, let's look at an example where there's not. Hi, Mr. McCusker. Let's look at an example where there's not. And so for this one, just very quickly, I have a TI Inspire tutorial. And so if you need that link, here it is. But I've already grabbed the important information. So we had an issue, I don't know, a month ago where we tried to use the TI Inspire to randomly pull values. I did some checking, and what happened, why we got all the same values is because we didn't reseed our computer, the calculator's computer. And so this is how you reseed. So if you're using the TI Inspire, reseed it first, pick a random set of numbers. As you can see, if the calculator starts with 1, 2, 3, 4, 5, so everybody's random numbers are the same because you're in seed 1, 2, 3, 4, 5. So if I plug in any other 4 or 5 digit number, my seed changes, so my random numbers change. That's why true random number generators don't actually exist as of yet. And then this is how you use random integer. You can either type in the phrase randint with the parentheses, or you can go to menu 5.1, which are your probability, menu 5, number 4, random. Yeah, menu 5.1, menu 5.4. Okay, so and you go there, you plug in all this information, blah, you have it. So with ours, we would be doing this question. In an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion where you get collectible cards of these following NASCAR drivers. A fan buys a bunch of boxes because she wants to collect all of her driver's cards, but she's surprised when it takes 23 boxes to get a full set. Should she be surprised? So let's create our simulation. Let's state, plan, do, and conclude. So we stated, is it fair? That's part of the problem. What is the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards? let's put each person as a number, and then what we're going to do is use the rand int 1 through 5, and that's this little symbol right here. Please don't forget to reseed before you do this. Pick any 4 or 5 digit number and you would have it reseeded. Why we can't do rand int and then 1, 5 and a number to purposely create a bunch is because we're trying to actually see what number we would have gotten in that cereal box. So let's see this simulation. And again, we're going to simulate it 50 times. However, just for posterity, I already simulated it for you a few different times. So it took 9 boxes to get a full set. It took 16 boxes to get a full set, 10 boxes to get a full set, and 20, and then 15, and then 22 boxes. So this is just the first few simulations. I can run this simulation numerous times to get a predictive model and to see, hey, do we see something that evens out? So here's our predicted model, and this is all 50 simulations done. So we never had to buy more than 22 boxes. As you can see, it's skewed very much. It's definitely higher on the left end, so it's skewed to the right, and that means more often than not you are buying less boxes than more, and so it should surprise her that it took her 23 or more boxes to earn all 5 sets. That should definitely be surprising. If it was truly randomized the correct way, then she should have gotten them earlier. And so that tells me that this particular cereal box company probably put a bunch of 1s or a bunch of 3s, and the more rare card was probably placed in there fewer times or something funny like that. But that's all we got. So were you able to interpret probability about long run relative frequency? Do you understand the myths of randomness and how we can extrapolate data that should have never been extrapolated? And can you use a simulation? Can you state, plan, do, and conclude to model chance behavior? All right, I'll see you guys in class.